We have an example problem here. A varying linear charge density of lambda equals negative 65y nanocoulombs per meter is distributed along the y-axis from y equals 1 to 2.5 meters. What is the electric field at the origin? Include the direction. All right, so let me draw a rough sketch. I don't have to go far out on the x-axis rather, because our linear charge is along the y-axis. It's telling us that it's distributed between y equals 1 meter and y equals 2.5 meters. Okay. Now, the other thing they're telling us is that this linear charge density is not uniform, meaning y, it's changing with the y position. So as y gets bigger, there's more and more negative charge. Okay. Line of charge. We know we can treat this as a bunch of charges, because that's what it is. It's a whole bunch of little pieces of point charge. And so each piece of charge will be creating its own electric field at the origin. So we will need to integrate. We need to add up the electric field due to each piece of charge. So ultimately, we need to figure out dq, r, and r hat in terms of one variable alone before we can integrate. If you watched the previous video, you saw that we got everything in terms of constants and the variable x because each piece of charge was a different distance x from the origin. So here, we want to find the electric field at the origin down here. We know this is negatively charged because they put a negative sign in there. That means any piece of charge I might look at. It doesn't matter which one. I'm just kind of marking out a few of them. Each piece of charge is going to be represented by having the amount of charge dq. Each piece of charge is a distance of y from the origin. That means r is going to equal y. Each piece of charge is going to have a length of dy because it's along the y-axis, so we're just giving it a little delta y or dy. If this charge, or since this rod is negatively charged, the electric field will point towards it. So each piece of charge is going to create its own electric field at the origin that points towards. That means r hat is positive j hat. Now dq, whenever we're doing linear charge density, dq is always related to the linear charge density. You can say it's total charge over total length, like we did in the previous video, or we can say it's that piece of charge, that point charge, divided by the length of the point charge. So last example was dx, and this example is dy. The reason they're different is just because of how this linear charge is oriented. The last one was along the x-axis, hence dx. This one's on the y-axis, hence dy. So I can say here, I'm just going to use this portion because I've been given an equation for lambda. That means I want to put dq in terms of lambda. So dq is lambda dy. Now we do want to be careful with signs, so I am going to substitute this in as the absolute value of lambda dy. Lambda is its own function, so we need to substitute that in as well. I already know the k is a constant, j hat is a constant. I'm going to pull those out. Now the absolute value, I'm going to have the 65y. Now nano is 10 to the negative 9, so I want to remind myself I need to put 10 to the negative 9 in for that. And I still have dy in here. So I can actually pull out the 65 nanocoulomb part, because again, I'm just doing the absolute value. And so that leaves me with y over y squared dy. But y, one of those will cancel. So this becomes just 1 over y dy. And we still have all these constants. Okay, let's scoot up a little bit. We do need limits of integration because we need to know where we're integrating. The integration is a summation, we're adding up, but what values, where are we adding up? Where is this charge physically located? And so our limits are always the ends of the rod or the line of charge. This lower limit will be 1 meter because that's where we would start as we move along the y-axis. And the charge ends at 2.5 meters. And so the upper limit will be the 2.5 meters. So now I'm plugging numbers in. So I have my K, I have my 65 nanocoulombs, J hat. I now have my integral of 1 over y dy. So that's the natural log of y. And we need to put in our limits. Oops. So we'll have natural log of 2.5 minus natural log of 1. But I happen to remember that the natural log of one value minus the natural log of the other is the same thing as the natural log of the first one over the second one. So I'm just going to write it that way. So plugging these numbers in, oops. I'm getting 535 J hat newtons per coulomb. We have, sorry, let me scroll up, 2 sig figs. So to round to 2 sig figs would be 540 newtons per coulomb J hat. Now notice we get the positive answer, the positive J hat direction, and that's because I did the absolute value of the charge. The charge density, remember, was negative, Had I left that in as negative, I would have come up with a negative answer, which would mean the negative direction downwards, which is not correct. So that's why it's good to plug in just the magnitude of the charges or charge densities and make sure you're accounting for the direction properly in your specific problem. We're going to do a problem next that asks about a point that does not lie along the rod, the axis of the rod. So in the picture up here, like a point over here somewhere. So the electric field would have X and Y components. So we'll look at that and how to integrate in a situation like that as well.